Alright, everyone out there in internet land, thanks for joining us. Today, as Neil's replacement, we have Sarah Yost. Take it away, Sarah.
Alright, good evening everyone, thanks for coming. As Balint said, my name is Sarah Yost. I'm the Product Marketing Manager for the USRP Rio, which is the National Instruments rebrand of the Edis Research X310 series. Thank you all for coming out tonight. This is our 7th Cyberspectrum Meetup.
Woohoo! Number 7! Yeah! Thanks.
So, as you all know, this event serves as a forum for the exchange of ideas and knowledge related to software-defined radio, and generally to get people interested and excited about the applications that can be realized with SDR. Engineers, students, hobbyists, enthusiasts, and people of all experience levels are welcome no matter what your hardware or software background. At the meetup, people from the community will have the opportunity to present their work, projects, and ideas to the group. So tonight our event is being sponsored by Edis Research. As you can tell, we're here in our building. And our first speaker is going to be Moritz Fischer, who is going to give us a little bit of show and tell. So everyone, welcome Moritz.
So I'm just going to do my usual little spiel for everyone. Thanks for coming along. If you're out there online, or even if you're in the room, please join us on Freenode, the Cyberspectrum IRC channel. It's really good if you're out there in internet land to ask questions of the speaker here, as well as to post any comments. So please join there. We have a growing following there, which is great. Thank you this evening to Edis Research for hosting and for the beer and pizza. If you didn't make it tonight and you're watching out there, I know who you are. You're missing out. So next time. Again, if there's something that you would like to present on or hear spoken about, please get in touch. You can join the Meetup page and post comments there on the forum and on the event pages themselves. And I've recently updated quite a few of the links here, but if you go to the pages link on the Cyberspectrum Meetup page, there is a link for each of the events, and under those pages I post the slides that the presenters have sent us, as well as the links to the videos as well. So it's a good resource if you want to, and helpful links as well to other resources online if you want to check that out. And the next meetup will be, that's supposed to be a hidden slide. Next one. No, back one. This, can you go back one, Sarah? This is supposed to read San Francisco. I think I got the slide mixed up there. But pay attention to the Cyberspectrum Meetup page, and then all this information is usually posted on Twitter as well at regular intervals. So this evening then, I think Sarah already introduced, but I was listening to a very delayed version of it on YouTube, so I wasn't quite sure you got this. Sorry, Sarah. No we have Moritz. There he is. If you want to follow Moritz on Twitter, there is his Twitter handle.
I roughly go on Twitter every 2 weeks, so there's not much to see.
Well, then there might be a 2-week lag time, but that's all right. So where was this taken, Moritz?
On vacation in France.
Oh, where were you in France?
In some old people place. It was really nice.
You were representing, good to see. And then next up we have Surya. I didn't think you sent me your Twitter handle, so I just put your name up the top. I hope that's all right. And where was this picture taken? You have an interesting background.
That was in Rajasthan, actually, like back in India.
Oh, right.
Yeah. So that's actually a palace, like, but you know, I wanted a thumbprint, like.
Sure. Yeah, good catch up.
Like.
Very interesting, mysterious background there. All right. So without further ado, then let's get back to Moritz, and we'll do a quick display changeover.
Welcome everybody. I'm kind of not so awesomely prepared because Balint walked up to my cube and was like, "Oh, you want to present your stuff you're doing?" And me and my colleague Martin, whose Twitter handle is here, we're basically doing this like Friday afternoon, an hour per week. So it's like we started 2 weeks ago, so that's about the amount of work that went into that. So it's not that well prepared, everything, and on a very, like, I'm going over things pretty high level. So what is DECT? I don't know, people around here maybe don't even remember those, because around here people use cell phones, I heard. In Europe, everyone uses them, like every household has at least one not all of them are from Siemens, but they're pretty awesome. There's like, you have like the Chaos Communication Camp, which is this outdoor hacker thingy, and like they run base stations. That was before OpenBTS, but they run base stations for that. You just bring your own phone. They're all compatible, and they all work together. You just bring your own phone, you sign into the network, and you can call other people on the festival campus. And, it's pretty neat. So, little disclaimer, I have no idea what I'm doing. I'm basically, so the goal of this project was like, how far can we get without actually reading the standard? We're just like dragging stuff together into radio, and I'm going to talk about what we did so far. So what is DECT? It has this like fancy acronym in Europe. It's like 1.88 gigahertz, 1.9. In US they have DECT 6.0, which is the same thing at a different frequency, but they put the 6.0 because, like, instead of calling it DECT 1.9, they called it DECT 6.0 because people get confused otherwise with smaller numbers not being the new stuff. Whatever. That's literally how they came up with the number. It's not at 6 gigahertz, it's 1.9 gigahertz. And yeah. So it has 10 channels. They're 1.728 megahertz apart. The bit rate is 1.152 megabits per second. Does TDMA, TDD, and FDMA. So it's, you have time duplex, frequency duplex, and then you also have slots you can share. And it's pretty trivial GFSK because those handsets have to be super, super cheap. So what we did is like a kind of duct tape receiver. Like, we don't really want to read much of the standard. We have those 10 channels that I mentioned. So in order to receive that very easily in radio, we make it 11, so we end up with 10. We channelize to 10 usable ones at 1.728. We resample, so we end up with 2 samples per symbol. We drag in the GMSK demod from the radio, and we skip all the fancy stuff such as equalization and so on. So, louder. Okay. So DECT burst basically, like, I just looked at what they call the P32, which is like the very basic one. They have 424 bits. They have a synchronization field that's supposed to be used for frequency offset correction and timing recovery. We just use the whole thing to correlate against it, and it just works. You have the header field, which basically tells you what the rest of those mean. We didn't read much about that because then you need to read the standard. You have payload, and yeah, and you have some CRC and some more CRC after that. Okay, so our approach was use the S field, correlate against that with the access code block that's in the radio, slice of 64 bits after the tag, which is your A field. Wow, the A field has a CRC, so we can validate what we're receiving and figure out whether that makes any sense. So we're like, okay, CRC. Oh well, the radio CRC doesn't actually do 16-bit CRC, so boost to the rescue. So we Googled a bit around for how to do CRC. We read the standard, fail, figure out the generator polynomials. We compile, we run, and fail, fail, fail. Everything's, wait, that doesn't look so bad, right? We're only 1 bit off. Close enough. That can't be coincidence, right? Okay, go back, read the standard, and the fuck? Why would you do that? Well, all right. So, victory. We take a B200, which we happen to have in our chips around here. Have our gigaset. We demodulate stuff with the radio users and minimal effort, and what comes out is already bits that are more or less usable. Since this is only like 5 to 10 minutes, I'll show a small demo and then stop there. This will probably fail because I set that up in my cube over there, and probably it will fail. All right, so I put a base station over there. You can trust me on that. So here you see like it's carrier 1 slot pair 2, 14 type whatever didn't read, and the A field. So it's basically running live in the other room.
Can you point at that again so I get a good photo?
Okay, well that you weren't supposed to see that, but one reason why I'm running that over there is what I'm going to show you if that ever stops. Okay, well that crashed probably. I just killed that. Okay, that. Never mind. You can anyway see more or less this stuff. So we have our USRP. Then we have the channelizer, which is basically just like you take your chunk of spectrum, which is like 11 times 1.728 megahertz, and you want to cut that up in like one channel-sized thing. So you take the channelizer, you connect them to the DECT burst smarts, which if I ever get that to right. So that's basically how it looks. DECT smarts. You have the resampler I talked about because we have 10 channels at 1.728 and they come out at 1.728. We want 2 samples per symbol, so we resample at 1.33. We correlate against the S sequence we took from the standard. Then we slice off 64 bits after that, or you could also slice at that point already the whole burst, that also works. Vector to stream, then we kind of shuffle it around, and here we check the CRC, and then we just throw it away. So that's pretty simple, I guess. Yeah, that's pretty much it. That's where we are right now. It's not a lot, but do people have questions on that so far? Yep.
So what's in the payload? I mean, you got a CRT check on the back of the data, so what is that actually carrying?
So we did the CRC check on the header, and then depending on what's in that A field, you have to reinterpret the payload as like MAC transfer messages, or actually also the B field, which comes after the A field, contains encoded voice. So if it's not encrypted, you could actually at that point just take it and stick it in a vocoder. So it's not that far away from working, I think.
Is there like, I'm thinking like Wireshark or something, certainly not for vocoder, but for other stuff, does that exist?
Yes, there's also like the DECT project. I think they used the hacked up PCM-CIA card, from my understanding, and there is like an entire Mac layer implemented in the Linux kernel. It's grossly outdated. I rebased it, and it actually compiled. So maybe at one point we are taking those data packets and then use like a simple character driver and then just feed it into the Mac stack and see what happens. I don't know if that makes any sense. But, yeah.
What could possibly go wrong?
Any other questions?
You had a couple of custom blocks there, right?
Oh yeah, they're horrible and I can't show the code. And that's also in the what's happening? So custom blocks is basically that one. That's a Python block that basically just slices off 64 bits and then looks at the A field and like prints out what you saw when it actually worked. It actually, I don't know if it will work again after crashing, but.
So if somebody from IRC is asking, can you hear voice, and I guess the exception to that is your encryption?
Well, we didn't look at that yet. That would be in the B field, so I didn't get that far.
But I guess one question is definitely encrypted. I mean, can you basically decode it out of the air, or?
You should be able to do that, yes. I mean, also, obviously, as you saw, like, the way we're doing this is not terribly efficient, because
Do you have to break the encryption in order to listen to that then, or is there?
most probably yes, but so from what I heard about DECT is like basically if there's one handset that says I can't do encryption, all the others stop doing it. So if you just misbehave, that might work. Then maybe there's like the better ones might just ignore the fact that someone can't do it and just keep doing it. But yeah, so so this one is basically the one that slices the stuff off, and that one does the CRC. All the rest is already in your radio, and you can just kind of drag it together. So at this point, basically, we could also just cut off the B field that contains the voice data, depending on what the A field tells us, what we're looking at. So
is it also standard vocoder?
Yeah, it's like G7, 21, and 26, I think.
So it's just support RDs for that? Probably.
Maybe.
Probably.
But so here, this DECT smarts is like a hierarchical block, and we use 12 of them in parallel, and we correlate and demodulate, and I think that's not very performance-wise, not very smart. So probably we should like look into that.
Can you show us that flow graph again, the original? Because it's
So basically, like we have 10 of them, so they're all run in parallel.
so that flow graph that you showed us before, they're all contained within.
They're all one of those. Yeah.
So
And
yeah,
you can also see how that it's pretty hacky if you look. Gee, okay, well, this X forwarding was a terrible idea. Well, you could see like in the other flow. Wait, I have to. Maybe not. So as you, I mean, this is like super hacky. You obviously wouldn't do it like that. It's just we wanted to get something working really fast. Yeah.
But is that all the channels, or are there?
That's one channel basically, and then you have 10 of those. So you could interleave them obviously and use the same block,
But 10 channels is like the entire search space.
the entire European one, yes, and then you can.
That's not bad.
Yeah, I mean also just 20 megasamples. So if you take like a 2B to 10 to get the European and the US one, and you're good. So it's definitely doable.
So, does the correlate access code do gating for the blocks downstream? from
Well,
it?
yeah, that's basically that's the start of burst tag here, and this one looks at a tag.
Okay.
Yeah, that's. We didn't really think the architecture through yet how we want to do the whole thing. It's more like, okay, we have something that works and drag it together. But
So that block though isn't actually doing gating. Is the field slicer then doing the gating?
yes. So basically that one here cuts off 64 bits, or I have another one that cuts off the entire burst, and at that point you'd hand it off to a higher layer. All right.
The person on IRC that asked the question said, "Thanks for answering my noob question."
Well, we're all noobs, right?
Okay, thanks, Boris.
Okay, so while we're getting set up, I'm just going to go ahead and introduce our next speaker. To give you a little bit of information about his bio, he is an embedded systems and software engineer with a focus on safety-critical software development for transportation and avionics and wireless communications. Most recently, he's been with Wind River Systems, where he worked on partitioning operating systems, separation kernels, and hypervisions for safety. Hypervisors. For safety and security critical avionics and defense applications. Previously, he worked on wireless and wireline communication software and systems at various companies including National Semiconductor, Conexant, Siemens, and Tel Labs. He has his master's in electrical engineering with DSP and communications emphasis from Clemson University, and BTech from IIT Madras in India. So.
That was a big one. I didn't expect you to read the full
Well, we know more about you now.
Yeah, absolutely.
All right. So.
And then, if you want.
So all of our Meetup presentations will be recorded and posted online, as well as streamed live on YouTube. The previous 6 events have already been posted in full HD. We have a channel on IRC called #Cyberspectrum, as Colin already introduced, on Freenode as a way for remote people watching to live stream, to contact the group and hear full comments, questions, and other audiovisual problems. Future Meetups locations will alternate every month between San Francisco and South Bay. The next Meetup will tentatively be held in June in San Francisco. Colin, do you have a date for that?
Last week of the month, probably.
Last week of June. The list of speakers and presentations will be posted in a week or so before the event. If you have ideas about future talks and presentations, let us know. We would like to thank you all for being here and thank our speakers tonight for their efforts and enthusiasm, and would especially like to thank Edis Research for the pizza and the beer.
Okay, thanks, Sarah. Grab some pizza and beer. All right, thank you, Surya. Take it away.
So, the only thing I would probably want to kind of mention is my last name is pronounced as Satyavolu for those who are interested. And I started this company this year in January, actually, with the vision to actually build enabling technologies for automated driving. That's the big vision, and I've been kind of digging into the happenings in autonomous cars and automated driving, and I was interested, and I see the need for the use case clearly. So I kind of started this company this year. You press here?
Oh, no. The middle button is the laser pointer.
Okay, this one's
Yeah,
here.
and then the right one is to go to.
All right, so before I kind of start talking about my proposal for actually doing automated driving, I wanted to kind of just give you some links. Like, I don't want to show the whole video. Like, most of you would have probably seen some of the user experiences with self-driving cars. There are plenty of them on YouTube, and these two are probably the ones I kind of wanted to point out. And in fact, like in the videos, you'll hear the person telling that the radar is actually very accurate, but still, like, they still keep facing problems, like, once in a while, and there's no way the driver can completely disengage and kind of sit back and relax, like, while actually, turning on this self-driving or autonomous mode, like, essentially. So then what's the problem? Like, one of the key things is, like, there's a design philosophy problem, I guess. Like, most of the autonomous vehicles are kind of designed for vanity rather than designed for safety. Like, what do I mean by that? Like, I'm actually traveling to Japan next week, so I can't help but talk about bullet trains, I guess, because I'm excited about it. And if you design a bullet train that comes to a safe stop in the event of an earthquake, that's designed for safety. If you're trying to see if you can design a track that can shake all the time, and you want to kind of design a vehicle that would handle the shaking all the time while it's running, like that would be designed for vanity. Like, so I don't see a point in some of the aspects of autonomous cars and self-driving cars, even the Google car that's being talked about quite a bit, actually. So I see a need for these self-driving technologies to mature into design for safety to realize automated driving use case. So I kind of wanted to propose something that would use simple guidance technology based off existing radar, but uses the structured environment with the reflectors, with improvement with radar technologies, like it should be cost effective. And it's a composable solution, like, and more importantly, like it can be verified, and how much ever length of the roadway you kind of put, like, you should be able to provide the assurance of safety, like, all through, like, and for all the time, like, for all people, like, and it should be a scalable solution, like, essentially. So the proposed solution is strictly based on radar for sensing and control based on wireless links, like, the hard real-time control, the real-time control of the hard real-time functions in the driving, like. That would be done over wireless links. So that would kind of give you a soft link kind of scenario, like, it's a hybrid between a train and a car. Like, you know, you can bring your own car, you know, enjoy the benefits of riding a train. You can kind of take it without having the last mile problem. You can, if you take a train or an airplane, like the problem is the last mile problem. You kind of have to get down at the station and you're stranded pretty much. Like, but if you take your own car, you can always get off the automated highway and kind of ride it home.
So, quick question. When you talk about wireless links, you're talking about within the vehicle, or you're talking about between vehicles?
Yeah, I'll talk about that. Like, it's between the, it's roadside to the vehicle as well as vehicle to vehicle. Like, you know. So if you, once it's in a platooning mode, like it will have to be vehicle to vehicle, and the leader would obviously have to be, you know, roadside to the vehicle. Like,
Vehicle to infrastructure.
yeah, exactly.
Can I ask a question? You mentioned platooning. What does that mean?
Convoying, like where vehicles are following each other very closely, and there would be the leader who would actually be in complete control, like, but the vehicle behind would be having the necessary lateral and longitudinal guidance and the control that would be needed to kind of follow at a safe distance back, like, essentially. So it's like, I'll show you the next picture, like, I guess, like, you know, where you have vehicles, one vehicle behind the other, car following it closely. It's a bit like the adaptive cruise control that you have today, but only thing is it's more stable and, you know, it has to be something that's more reliable, like the link has to be more reliable.
And before, you mentioned that problems have occurred with existing technology. Can you give examples of where things have actually gone wrong?
If you're talking about, yeah, I mean, maybe I can show you the video, but pretty much like, if you're talking about fully disengaged automated driving, like, you know, where the driver can kind of, even Tesla is saying, like, you know, the driver would have to kind of switch some button, like, so that he can get the liability, like, you know, he kind of had to judge the weather and everything. I don't know how he would do that, but based on that, you had to kind of press some button and kind of take the liability to allow the car to drive autonomously. Like, you know, that's all, you know, BS, like. So ultimately, like, you kind of, the question was, like, what was the question? I kind of forgot, like, talking about that. But,
well, first with the platooning and then things that have gone wrong.
yeah, the things that have gone wrong are, like, there's no way to kind of achieve fully autonomous driving, like, you know, where the driver can be fully disengaged. So then this is like structured environment with radar reflectors along the pathways, along the guided pathway, like, essentially, to provide accurate path planning as well as trajectory tracking, and a dedicated wireless channel for control functions. So this would be a dedicated spectrum. There's actually already spectrum allocated in DSRC, like, for safety communications. Like, we could probably reuse some of that, like, actually for you know, safety critical control communications purposes. And then out of any other communications like network management of roadside infrastructure, or, you know, any other communication that would be non-control related would have to be done out of band. Like, this is to kind of, you know, promise the reliability. And it relies on high specificity, high accuracy, and low false alarm rate radar sensing, including detection, training, and speed estimation. And there are a lot of advances in radar technology, particularly, you know, silicon-based radars are kind of, you know, providing low cost, especially like the, you know, frequency modulated continuous wave radars implemented on, you know, BiCMOS technology, or even silicon germanium technology is kind of, you know, arriving at cost points like where it should be possible to achieve something scalable, like with low cost radar technology. And then one of the key things about the control communications is, like, it has to be hard real time, like, you know, because it's used for controlling hard real time functions, like, which basically boils down to bounded worst case latencies. And it also talks about platooning, like, because if you have vehicles following close to each other, like, the perception of the follower vehicle is pretty much limited to vehicle ahead, like, you know, so it can't see the whole pathway, like, so at that point, like, it has to be the leader who would have to guide the one behind, like, so, and it also improves the utilization of the highway, like, because you can kind of reduce the following distances, like, when you kind of establish the platooning mode with the high reliability. So this is kind of like, you know, what I'm talking about, like, you know, there will be some reflectors placed along the pathway, like, which should be like the radar reflectors that provide you the necessary cues for the external structured guidance, like cues. And then there will be reflectors also placed behind the vehicle ahead, like this would be used in platooning mode, like where the radars would be used for actually using the reflectors as cues to actually establish a soft link. And then there will be a control channel. Like once the link is established, the homing guidance takes place and the terminal rendezvous is established. Like there will be a wireless link to kind of allow control by the vehicle ahead. So, and then there's the roadside to vehicle control that will be happening, and also vehicle to vehicle control when in platooning mode. Like the control would actually be handed over to the vehicle ahead, like when you're following closely with the board. And what else did I miss? So there will be roadside reflectors, which I already talked about, and then there will be infrastructure that I already talked about. Okay, I think that's it. And these are some of the advantages of radar for sensing. Like it's easy to ruggedize. Like we were talking about just metal reflectors. Like these are we should be weatherproof. At least definitely weatherproof than paint that you use today. Like, so these are just metal reflectors, and spectrum is already regulated like a. And in fact, DSRC channels are kind of, they already have the spectrum for short-range communications, like, and also like radar has been used in transportation quite effectively like, for a long time. Like, even in avionics, like the ILS instrument landing system, and all kinds of weather, like depends on radar technology like, to kind of do landings even in hot weather conditions. So, and then millimeter wave FMCW radars have high detection probabilities, especially with metal reflectors and weather tolerant. In fact, in the airport, like they use millimeter wave scanners to actually detect metal objects like inside your suitcases and things like that. And these are some of the requirements of the wireless control channels, like that you use, like. Protocols that you design like would have to be hard real-time periodic control of driving functions. You have to be able to do periodic control, and then timing would have to be synchronized and deterministic worst-case latency. And reliability, maintainability, and availability of the control channel would have to be established. Like this is again like boils down to the reliability of the whole platoon structure itself.
Structure cope with, I guess, heterogeneity in vehicle performance? Like you have a bunch of people with Mustangs and then somebody in the middle with a Prius.
Yeah, it has to be standardized. The geometry has to be standardized at least. Like, so that's why I'm using reflectors actually. Like I'm not depending on the vehicle's geometry. Like I'm depending on
the vehicles themselves. Once they're outfitted with these control systems, like is it planned to have the algorithm cope with differently performing vehicles so that you like let all the fast cars group together, all the slow cars group themselves together?
Not really. Like, so, I mean, of course, like once this has to be commercialized, there has to be some certification body that would have to certify it for an automated highway driving, like actually for the vehicle, and that needs to have minimum speed requirements. But it's overall speeds, like the system-wide speeds that I would be concerned more about than individual speeds at that stage. Like so, but every vehicle has to have a certain amount of power to pick up and acceleration power and all that. But also like geometries, like I don't want to depend on the vehicle shapes and sizes and all that. Like the radars would have to be placed. The radar geometry would have to be fixed and standardized, as well as the reflector geometry would have to be standardized. Like so. At a particular height, at a particular distance. At least there may be two different types of geometries, but not more than that. Like maybe for trucks, like you want to have a different geometry than cars, but not each car has its own. It would be too difficult to handle.
So what happens if someone were misplaced and on purpose?
No, I mean if you want to get on the automated, that's why it has to be certified for automated highway system, and it has to be something that would have to check out. Like
if someone moves it. Right.
Malicious.
While driving or malicious?
Maliciously.
I mean, if there are trucks going on the highway, like what if that guy rams onto your car? Like, he can kill a lot. Trucks have actually like a lot more kinetic energy than a Hellfire missile. Like, so there's a lot of damage you can do with a lot of things on the roadway. Like if you're talking about malicious, but some amount of it would have to be through certification or driver certification or things like that. But other things like it would have to be checked out, maybe put some camera before entering the highway just to kind of check the geometry and things are okay.
Presumably you could incorporate something like RAIN from GPS, where you self-check a surplus of sensors, right? If there's something anomalous, you can reject it.
Yeah, exactly. So, and then that's why, like, one of the things with the radars is, like, today's radars, like, they kind of work with a very large cross section, like, they're not very specific, like, that's where the reflectors with a lower cross section kind of improve the accuracy of range, velocity and azimuth determination. You know, there are all kinds of radars that are already placed on a lot of the cars that have these advanced features, but they detect anything from a car and a truck like that, but they kind of have an assumption that it's a particle in space, like it's not really true, like once you're talking about close distances, like where the cross-section can be comparable in the magnitude
versus Hummer.
Pardon?
Motorcycle versus Hummer equipped with this sort of thing.
Yeah. And then we're talking about infrastructure to wireless vehicle control as well, like, you know, again, the same kind of things, like, then there should be, you should also think about reliable handoff of control link, like as the vehicle passes through the guideway, like once you have a control link from the infrastructure unit to the car, and then the car passes from one, it's like a cell phone passing to the base station, maybe from one base station to another, like, but at higher speed, I guess. So that thing needs to be worked out still, like, actually. And then again, like the same thing, concepts as a cell phone, like spectrum management techniques to enable reuse without the loss of reliability, and then the guidance law that would be needed to allow the vehicle to drive to the guided pathway. We'll talk a little bit about that as well, like as we go. I will talk a little about the radar technology and a little about guidance, but you know, the whole problem is pretty big, like the problem space, like I don't want to get into complete detail in every aspect of it, like so. But today I will talk a little about the radars and the guidance technology. And we're talking about the homing guidance. This is for platooning, like it has to be reliable homing guidance and the stabilized rendezvous. But once it's in platooning, like we're also talking about stability of the rendezvous, like, you know, it has to be maintained, like as the vehicles kind of go drive through the freeway. This is repeating some of the things that I already talked about, I guess. Let's skip this. And one of the key pieces is the radar, like, you know, because we're going to use that for, you know, sensing, which would be used for guidance purposes. And one of the things that I'm excited about is the phased array radar, like, which would kind of provide you with the beamforming, directional beamforming, as well as beam steering, electronically steerable beams. Like, so I wanted to talk a little bit about phased array radars today. So essentially, like phased array is like a spatial filtering techniques that would kind of use some weights and phase differences, like for different antenna placements, like actually to kind of create a directivity pattern using constructive interference and destructive interference at non-desired angles, like essentially. And then if it's implemented, it can be implemented either in the receiver or the transmitter. If it's implemented in the receiver, it's a bit like the rate receiver, like which is probably being in use for quite a while, like especially in the cell phone industry, where you use the rate receiver with the weights, like to kind of, you know, the receive channel. And then if it's implemented in the transmitter, it would be spatial power combining to kind of achieve directionality. So essentially, like it's making use of the path length difference, like and kind of compensating it with the phase difference to achieve a maximum constructive. Once all the three antennas are kind of transmitting in phase, like let's say, it would be theta equal to 0 would have the maximum, like, you know, constructive interference, like, so the maximum would be in this angle. But once you want to kind of, you know, change that maximum or steer that maximum, like you want to kind of introduce a phase to compensate for the path length differences, like, you know, this is the path length difference between this and this, like, so the kind of phase difference that you want to kind of introduce between the two would be 2 pi by lambda. This is basic geometry, P sine theta, like essentially. So this is the basics. Like same thing. Like if you want to look at a planar array, like you can talk about an elevation angle and an azimuth angle. So in that case, like the phase difference would be a sum of the elevation phase and the azimuthal angle. The component for the azimuthal angle. So this is what I talked a little bit already about. Like, but basically, if you use an isotropic element, like there's no directionality. Like if you use single antenna, like any side would be the same. Like there's no beamformer. And then you could have a passive phased array or an active phased array, depending on where you introduce the phase control, like, or the phase modulation, essentially. If you kind of do that before actually before constructing a beamform or the waveform, kind of, then it would be an active phased array as opposed to a passive phased array where it could be done just before transmission. And of course, it's a bigger subject. Like so you can go into any depth in this. Like I'm just trying to provide a little basics on this. Like this is the directionality that I was talking about. There will always be side lobes like that will be introduced, like which with a certain impulse response. This is of course the theoretical part of it. Like once you kind of introduce weights, there will be a little different side lobe response as well as you can play with those to kind of achieve a lot more desired response for the antenna. Like using the weights and the geometry, especially like if you want to use a broadside steering, like you kind of do a 90-degree steering, like there will be something analogous to an aliasing, like there will be grating lobes like on the sides. And by choosing, you can also weight each of those to kind of achieve, and also modify the geometry of the array to cancel out energy in undesirable directions while maximizing energy in the desired direction. Like so, you could have more beam control, like essentially. There are quite a few weighting methods to control the side lobe levels. Like this is going down to the filter design techniques, like Dolphin and Chebyshev, so Shelton of polynomial method or linear mean squared error. It's a little more like an adaptive technique. This is one of the links which I found very useful. Like there's some antennatheory.com has a quick reference for good fundamentals there. This is like an FMCW example. Like there's a single antenna. Like this is probably how an FMCW radar block would look like. There would be a waveform generator and a linear LNA, and then a bandpass filter to kind of then it will be mixed with a local oscillator to kind of do an up conversion, and then pass through a bandpass filter to kind of filter out any component outside the frequency range. And then there will be some phase calibration, and it will be amplified to the RF, and the RF will be amplified and kind of transmitted to the antenna. And this is the receive path. Like actually, this is pretty straightforward. Like in a down conversion, and then low pass filtering, and then the back of the PC will actually do the signal processing in baseband.
It's interesting to me that you're drawing all this, and it's still the very traditional phase array where the phase shift is done in the analog domain. I'm just wondering, since you're planning for the future, is that still the sweet spot, or is it?
No, this is not even having any phase. Like this is like a single antenna thing.
Yeah, I was looking at the diagram on the right, I guess.
Okay, yeah. This is the one that would have. This is still using like analog, like, but you can use the digital, direct digital synthesis and all that, like.
Sure.
But I'm just showing an example right now, like, So this is like using the what's it called, like PLO, like the phase.
Sure.
With the phase local oscillator.
I'm just curious when that sweet spot occurs, right? Where it always becomes
better
to do it in the digital.
Yeah, better do it in the digital domain. Like actually, that would be have more control, and that would be allowing, like, again, like software-defined radio. You can do a lot of things that in software itself, like to kind of do the control. So
price and antenna design, right? Price and antenna design. If you're going, especially depending on what frequency you end up putting this at, like you can make really, really small antennas very cheaply. So.
The the millimeter wave stuff chips is don't put the antenna on the dime.
Yeah, well, exactly.
Sorry.
Okay.
Sidebar.
No, I didn't get like when you say like you're saying like you can create cheap antennas, or you're saying like it would add to the antenna cost. I didn't get.
I think going forward, price is obviously going to be a big motivating factor in how the standard evolves.
Yeah, exactly.
And so, you know, if you can save money by doing an analog antenna design that does some of your down conversion versus making a flexible front end to do it digitally, I think that's going to probably win out, even if you have to upgrade equipment in the long run.
Actually,
At
it's
least
the other way
on the
around. I thought like even though digital, digital like it will fall in prices like much more.
Yeah.
And experience, intuitively speaking, like if you try to do things in analog, like it's kind of hard to replicate things. So
It all depends, right?
yeah, it becomes more of an art like once you kind of get into the analog domain. Like, so again, like this is doing the same thing, like you're doing some phase control on each element antenna path, like essentially, like, and then it's doing a bandpass filtering, like after doing a mixing, like, to kind of pick up the frequency, and then again, like IF, like there will be some more mixing, like then kind of has a 6-pole bandpass filter, and the filter design is one key aspect of the antenna design, like. Poles basically like is like a zeros in the impulse response, like so you can kind of play with that to kind of achieve the desired response like that you want for your antenna. So that's part of the design part. Now I want to talk a little bit about guidance as well. Like though I don't know if how much of this audience would be interested in that guidance part, but I just want to kind of give an overview because that's a key part as well. Like when I believe in structured guidance for achieving automated driving. Like there are challenging unstructured environments where you can kind of design some guidance system that handle unstructured environment, but I don't believe that you can ever achieve all kinds of like you can handle all kinds of unstructured environments. Like so, one of the things is like the present day lane markings, paint like that would be used quite a bit. Like without telling like even how much of an unstructured guidance you use, like you're still using those lane markings to some extent, like with today's self-driving car technology. And magnetic guidance markers, these are other things like they're also you can use GPS even, like but again like accuracy falls, like because obviously like when you're talking about using GPS for deciding close range distances for your bearings like or angles, like there are problems with that. Like there are proposals on those ends fronts as well. Like there is some magnetic guidance. This looks promising. Like actually, like though one of the problems is with the assurance, like because magnets do wear out. Like but people's, I mean, again, like it boils down. You have to prove that it's reliable enough at least, like with magnetic guidance, and some of them are being used actually in transit applications in some places, like with magnetic guidance markers and automated transit applications. But I propose a radar guidance with structured placement of reflectors. And again, this is repeating some of the things, like it uses a millimeter wave low-cost FMCW radar and phased array for offer flexibility for actually steering the beam and offering flexibility. Advanced path planning with the look-ahead distance, and safety assurance problem is primarily shifted to the onboard guidance system, like the software that's actually on board, like will be the one that would have to be really certified to prove that it's doing what it has to do, essentially. The assurance problem is a little more easier, relatively speaking. These are some of the, path tracking algorithms. These are some basic algorithms at least. Like I just want to kind of give a overview of that. Like if you have this vehicle kind of here, you can use a caret, simple caret, like where this is the look ahead distance, and then they have a caret point, like that's the goal point, like where you kind of have to arrive, and there's the orientation error. You just turn it around to go there, like go to the goal point, using the proportional control law, like it's proportional to the orientation error, like you just turning radius is basically proportional to the magnitude of the turn. Or you could do a pure pursuit, like where you're trying to kind of steer along a circle that passes through both the goal point as well as your current position, essentially. And the turning radius would be computed as 2 times the x difference divided by the distance between one point and the current position. And then there's vector pursuit, like which kind of gets a little more interesting because you don't want to just get to the goal point, but you also want to get there with the right kind of orientation. Like there will be an orientation that you want at the goal point as well. Like. So this uses a theory of screws, like any rigid body can kind of has 2 kinds of velocities. Like one is the rotational, and the other one is the translational velocity, essentially. So it calculates 2 screws, like one for translation, the other for rotational orientation to arrive at the goal, and uses a sum to determine the required instantaneous velocity, like essentially. So it calculates. So these are some of the equations. Like this is the rotational and this is the translational component. Like you can kind of represent the screw like with the omega s. Like that is the rotational component, and SOH is the translational component. And S0h equal to this is the vector addition actually. So this is like if you're kind of trying to rotate like this, the translational part is kind of proportional to the pitch like of the screw as well as the rotational direction that you do. So anyhow, this is just an introduction. Lots of interesting problems to solve. Like the main goal of this presentation is to kind of present the vision of the company that I'm kind of trying to run and kind of trying to create. And right now I'm working on some SPI proposals, and I want to kind of generate interest and see if I can form a team or kind of generate any interested people, interest around people, so that they'll be interested in kind of pursuing the same mission, I guess. So anyhow, thanks for listening, and welcome to ask any questions right now. There are, of course, a lot of other problems that I didn't delve into, like even platooning, like how we would do the guidance and all that, like and kind of establish them under WU, like and how we would do the guidance, terminal guidance, like when you kind of achieve at the right position and all that. There's a lot of problems to solve there, like so. It's already quite a bit, like time, in the interest of time, I didn't go to delve into everything. So the goal is like the basic use case is like let's say like you want to go from San Francisco to Disneyland, like let's say you enter in San Francisco the automated highway system, and you can kind of give control to the car and play whatever game you want in the backseat with your kids, like, and kind of just get back to the steering wheel only when you want to get off the highway system. That's the basic vision, like of how the use case that I'm kind of chasing right now. So yep, that's pretty much it.
You talked a lot about wireless communication links and them being hard real time, which pretty much to me implied that it's life safety critical application.
Yeah, exactly.
Do you think that's achievable? I mean, wireless links are by their nature, right? They're not 100% reliable, so.
Yeah, they're not 100% reliable, like, but obviously, like, this is theoretically speaking, like, where the noise and inter-channel interference is controllable, you should be having fixed, and the protocol kind of supports hard real-time periodic communications. You should be having bounded worst-case latency. But how much you can kind of control inter-channel interference and interference from other wireless transmissions, that's why it has to be regulated. Like, there's no way you can do that in an unregulated channel. Like, So, but again, this has to be done. Like, I mean, it's done in small scale. Like, automated guided vehicles are there, like in factories and all that. Like, since a long time. Like, they do wireless control. Like. But reliability is the key thing. That's a good point. Like, it has to be something that has to be proven, like both through theory as well as testing.
So is your research more on the radar side of things, or like the 802.11p standard?
No, not the 802.11p. Like, though I'm kind of attending those. Like, I'm focusing more on the radar for guidance right now, and also like I want to kind of use wireless control, but it's not going to be directly 802.11p. Like that much I can say, because the Mac has to be changed. It has to be probably more like a TDMA Mac, like with time
So do you think that standard is going to prevail to be used in card-to-card communication, or do you think it's kind of going to fade out?
I mean, I don't know too much about the use cases for that, like though there are apparently quite a few, like, it depends on, it can be a little, I mean, maybe the use cases would die out, like, but its standard would survive, like a lot of things.
I guess some of the researchers that I've worked with are trying to evolve that standard to be set for card-to-card communication and try and get it to where it has the latency requirements and the priorities set correctly to work for card-to-card.
But again, like, finally, like, we have to decide, like, when you say communication, is it going to be used for hard real-time communications? If that is the case, like, I mean, it has to be strictly for that, and, there's no way you can achieve that as well as do other kinds of things with the same thing. Like, at least, like, it's not been done in any transportation application where it's completely unregulated, like, it's a safety critical issue. Like, and even if you use a car for, let's say, like, there should be thousands of cars on the freeway, and every car has to work, as well as for a number of years, right? Like, so the odds are too heavy. Like, if you introduce any sources of error, they'll definitely go wrong. Like. So, yep. Any other? That's pretty much it.
How do you authenticate vehicle to vehicle messages?
Vehicle to vehicle, like, I mean, this is like for control communications, right? So there should be a link established. So there would be some initial authentication, definitely. But it's not really that much of authentication problem. It doesn't matter like which vehicle you're talking to, because it's strictly used only for hard real-time communications. It's something that's regulated channel, and I don't think you can really hack into that. Like, if somebody can hack into that, it would become more of a safety problem than a security problem.
Yeah, if somebody hacks into it, then it causes safety concern.
Yeah, it causes safety concerns. So that's why, like, I mean, FCC regulates a lot of the communications. So a lot of the transmitters are regulated in a way. Like, otherwise, like, you can crash planes, like even today. Like, if you kind of can transmit with the right amount of power and with the right amount of with any frequency you want, like you can jam communications that are used by aircrafts to kind of crash them. So you can kind of create some spectrum management techniques, like spectrum techniques and things like that will be anti-jamming capable. Like, but that's a different problem.
And then probably building in a bunch of fail-safe control logic that
exactly.
In case of poor signal quality, just fall back.
A
mechanical, be safe.
Yeah, be safe. Like, at least get off at the nearest exit. Like,
let's tell the driver he's driving again.
Yeah, exactly. I wouldn't want to do that actually, because on the automated highway, like, I want to be purely automated. Like, I don't want regular, manual drivers also going on the same path. Like, so I would probably want him to get off the freeway at the nearest point. Like. Yep. So, all right. Thank you.
Thank you very much.
All right, so for our last speaker tonight, we have Balint, who's going to present to us on something interesting and hacky, I'm sure. Balint is our SDR evangelist and enthusiast for Edis Research. And yeah, he's Australian and pretty awesome, so enjoy.
Thanks, Sarah.
Put me on the spot.
So I guess I finally emerged from behind the camera. Good evening, everyone. I'd like to talk to you this evening about how you can go about streaming some live video using GNU Radio from one SDR to another one. And so I've got a couple of slides just to give you a bit of a feel, a bit of an introduction, and then I'll actually do some live demos. Fingers crossed they will work. So if we consider both sides, you've got your transmitter and your receiver. The basic steps that you go through are image acquisition. So in this case I have a webcam. I'll show you in a minute when I pick the webcam up and the object that it's attached to. Once you actually do your image acquisition, then whatever API you use will give you some raw data that represents your picture. You then turn that into packets, you hand it over to a modulator, and then it goes out over the air. On the receiver side, you receive those packets, you demodulate them, you actually detect the presence of a packet, take the payload out of that packet, reconstruct your final blob, your final payload, and then you can hand that off to your GUI to display it on the screen. And there are certain subtleties in each of these steps that you should take into account. Tom, I wanted to ask you, are you still looking at the channel?
I am.
Okay, can you ask everyone if the AV is still good? Sometimes the AV goes funny. So the way I've done it here is, I've got this webcam, and Linux has this API kernel layer as well as user mode component called Video for Linux. And it abstracts away all the details about many modern video capture cards, TV receiver cards, and webcams. And many webcams nowadays will stream in two modes. It'll either give you raw, uncompressed frames over the wire, or they do hardware motion JPEG compression on the device itself. And that means that it'll take a still frame, compress that using the JPEG codec, and then give you that compressed frame. So there's no motion compensation or anything like that. But on newer webcams like the Logitech C920, this is not this one. The C920 is actually what we use for the live stream. This is the 9000. It does H.264, so it does that temporal compression as well. In this case, I'm going to show you this webcam using MJPEG because obviously you want to send smaller sized pictures over the air. So the next part of this is actually using the API. So there's this neat Python v4l2 capture library. It's a Python abstraction of the v4l2 interface, makes it really easy to set up your capture device and then receive frames from it. And then once you've got that payload, then you can treat it like any other payload. In this case, it just happens to be a picture. So in preparation for transmission, the idea is we want to send bursts of packets, bursts of information. We need to packetize all those individual frames. And you need to add a header onto your payload to describe, for example, how long it is, if you're going to use forward error correction, and so on. And in this case, we want to keep the burst small. So like sending packets over an Ethernet network, there's usually some sort of maximum transmission unit or MTU. So here we can determine some MTU as well, the maximum length of a frame. And so if your image or your payload is going to exceed that length, then you fragment them into the smaller packets, just like UDP does. And then you would send that over the air, and you would reconstruct that in the receiver using that header information. But what's interesting about this particular setup is I've separated the transmitter and receiver section as well as the image acquisition and reconstruction. And they're separated on the local host simply through a UDP socket. So in any of these applications, you can simply throw away the image acquisition and replace it, say, with audio acquisition. So you could stream audio across the interface, or you could hook it up to a virtual Ethernet interface and send that kind of data across. The virtual Ethernet interface is interesting, a little bit more complicated, but it's certainly doable, and we've tried that. So if you have that kind of network interface, it's a nice abstraction. So the process here is that you essentially grab your entire image buffer, you segment that into MTU sizes. For the image application itself, you add a header for that fragment, so you say maybe what kind of image format it is, the resolution, and then what fragment offset it is within the entire frame, entire payload, so that the receiver can reconstruct it. And once you've got your fragment, then you add your header for transmission. So like in the network stack, the OSI stack, this is the lowest, the second lowest layer. And so you add your total payload length and the CRC, and then that'll be sent off to the modulator. Now, in this actual application, I'm going to show you some source code as well. These are the details here. So at the bottom, if you think about this inverted on the OSI layers, you've got your image fragment. You send over the 4cc, which is the 4-character code that describes the compression used, the resolution, the sequence number, which is like a bit of your frame count, the total size of this frame, the fragment length of this fragment that you're sending, and the offset into the entire payload. And then above that, you send your top level packet header, which is going to be the first layer over the air. You've got your preamble, your access code. And the access code is important because your receiver, when it's demodulating, is going to look for that fixed pattern that's going to demarcate the beginning of a new packet. And so your receiver will think, oh, I can see the access code, so now I'm going to start decoding that payload until the end, which is then set by the length And these packets are actually scrambled or whitened as well, so that index is set in there, and then the CRC is put on the end, so that the receiver can determine whether it received a correct frame or not. So this is essentially error detection. There's no forward error correction here yet, but this is actually already provided by GNU Radio. It's in the Python code, the packet frame Python code, and it works quite nicely in sort of simple setup. So in terms of the modulator, this is where you can think about how you're going to design your communications channel. Here I've kept it very, very simple, but you can have certain considerations like what is your raw channel bit rate going to be. And this is particularly important, and you'll see why in a moment, when you're trying to run perhaps your transmitter on a device which is power constrained and CPU constrained. An embedded device, for example, not just your average PC. And then as you choose your modulation scheme, you need to figure out how many bits per symbol. So, you know, if you're using BPSK, then you're going to have 1 bit per symbol. You're going to use QPSK, then it's double that. You go crazy with QAM, then you can get even higher, but there are particular losses associated with that. You decide whether you're going to go bursty transmissions or have a continuous stream into which you inject packets. If you're going to whiten it and scramble, as I said, do the error correction, and so on. And this is important because in the case of video, video occupies a fair amount of bandwidth. It's not like just small text packets or low bitrate audio. Video can occupy quite a bit. And so you need to squeeze quite a bit through your pipe. And I sort of started off at some lower rates, and then I eventually got some high rates going, and I'm going to try and push that a bit further. For the demodulator then, you've got also a lot of considerations, and GNU Radio can help you account for most of these things. You need to detect some frequency offset between your receiver and your transmitter. You need to correct for some phase offset, and then when you actually do the last stage of your demodulation, you need to track the symbols that are being sent by the transmitter and do the timing recovery so that you sample at the appropriate time. And then if you want to go really fancy with, say, forward error correction, you can do soft decoding and maybe have a Viterbi decoder if you convolutionally encoded it to begin with, which is something I will look at. So the last stage, once you actually get your bits out, is looking for that access code, as I said, that demarcates the packet. You begin decoding the packet, you extract the payload because you know how long it is based upon the header, and then you can compute the CRC of the payload that you just received and compare that with the CRC that was sent over the air. And if it's the same, then you have a valid packet. If they're not the same, then in this case you throw it out because you don't have any forward error correction information to correct any errors. So one thing that I'm thinking of looking at is adding a convolutional code and a Viterbi decoder on the decoder side, and that might help. But just for a simple test, this works. So once you've got your decoder in place, then it's a matter of creating a parser to actually extract the information and do something useful with it. So usually you have a state machine. If you've actually segmented your payload into smaller chunks that need to be reconstructed, then you wait for an incoming packet. In this case, it's sent over that UDP interface again. And then you begin construction of a new image frame, or if you're already in the middle of constructing one, then you wait for the next segment to come through and add it onto your buffer, and so we build your buffer up. But let's say we have an error that's come through a packet and that packet gets dropped. Then you've got a discontinuity, so then you have to decide, oh, I'm going to still leave that gap in the image data and then continue constructing it and then get a corrupted frame, or you just reset the state machine and then you wait for the next frame to begin. So certain considerations like that too, and that depends maybe upon what kind of compression you're using. If you're using temporal compression like H.264, if you end up having an error in a frame, because it's temporally compressed, you're basically going to have video that looks pretty weird and corrupted for perhaps potentially many seconds before the next iframe is sent through. Well, it depends. That's what I found anyway. If the webcam only sends iframes every so often, then Ian, what are you thinking? They're smiling and grinning.
It's fine. Just talk about radio, not video.
No, go on.
There's very limited corruption because the ability to use the syntax of H.264 will limit the run of errors like that. So
H.264.
Slices and stuff. H.264, sorry.
Well, maybe the open source decoder I used wasn't performing particularly well. So yeah, so hopefully that's given you a bit of a flavor. Now I'm going to change the display and actually show you some live demos and some code. Any questions so far?
So have you considered packet and packet attacks yet? Just throwing that out there.
I think that's slightly beyond the scope of this.
Reset the section and wait for the next person.
Don't want to hear that.
So
Shush! Damn it. I don't have control.
This is going to happen again in a few seconds.
There we go. So what I've got actually is I've got my laptop here running as the receiver, running GNU Radio, and I've got this B200 hooked up as the receiver. And over here, what were you saying, Maurice?
So many tabs. Such a professional.
Oh, really? Okay. And for the transmitter side of things, over here, hopefully, more or less, you can see this. I've got this drone, and part of the work that I've been doing here is attaching. Hopefully, you can see on the bottom here is the E310, Meetup E310, which is the latest embedded version of the USRP. So this is actually an SDR with a dual-core ARM processor on board running Linux and GNU Radio, and also FPGA Fabric. So this one I've got strapped there, but I'm actually using this one to do the prototyping. So on the very front of the drone, you can see there's that HD 9000 webcam, and that's hooked up by USB to the... Huh? No, come on, share your comments.
No, we're just hoping that there's no way that drone could start with the next one.
I have actually flown this with the X310 and done the video streaming, so it does work. But this one I've got hooked up by the serial console, Ethernet, USB to the webcam, and power. But I'm just going to put this back here on the chair. And on the other side of the E310 is, of course, the antenna through which I'm going to transmit the modulated video. So what have we got? So the first thing I'd like to show you is how you can create some flow graphs to do the modulation and demodulation. Would somebody just mind? Oh no, I can do that. I'm just used to being behind the camera and checking that everything looks good, but I think it does. All right, so this flow graph here, let's have a look. This one here is actually a transmitter. No, it's not. It's the receiver, sorry. Where is it? So this is a simple transmitter. I'm not actually going to run this one, but just for the sake of example, remember this is the transmitter side, so you open up a UDP socket to listen on, and that's just going to accept or use a payload. It's going to go into the packet framer. The packet framer is what turns it into a packet amenable to be sent over the air. So it's going to add that access code, preamble, put it in the length of the payload, insert your own payload that's come in through here, and then put a CRC on the end. And you'll notice that these are actually PDUs, packet data units. And so these are particular kind of messages that contain the payload plus some metadata to say how long it is. Once you've framed it up, then it'll go into this tag string block, and that'll turn it from a message into the traditional data type in GNU Radio, which is a stream of samples. In this case, they're not actually IQ samples, they're streams of bytes that you had in your message. That then goes into this GMSK modulator block, and internally it's a whole bunch of other blocks that does unpacking of the bytes into bits, then does some frequency shift keying, and then pulse shaping to turn it into GMSK. And then out of that you can see that it went from bytes, which is pink, into blue, which is complex samples. You adjust the amplitude of the signal, put it through the burst tagger, because in this case, whenever you have a packet come in, it'll just go through the flow graph and then go into the USOAP sink here, and then it'll just send out a burst of information over the air. So there's not a continuous streaming thing. When you get a packet, you essentially get a burst, a transmission out of the radio, and then it'll fall silent again. So there's another way of doing it too, which is instead of having these bursts being transmitted when you get a packet, you're just continually sending data, and you might transmit some pseudo-random noise, pseudo-random sequence in there, and then when you get a packet coming in, you actually insert it into your stream, and then transmit that out. And that's what I've done in this other example. So on the receive side for this one, the idea here is that it's very simple, and this is doing all of the modulation. For the receive side, this is essentially what it is. So you have your receiver here, XDR here. You can take that straight into your GMSK demodulator block, and internally inside it's got a lot of other blocks set up. This is more like a hierarchical block that actually does quadrature demodulation, the filtering, slicing, and so on. And this will continually be streaming out a sequence of bytes. Now, if there's nothing actually being sent over the air, what comes out of this block will be garbage, right? Because it's basically trying to demodulate noise. But if there is actually a signal there that has sufficient energy for this to decode properly, then what comes out of here will be more or less some intelligible sequence of bytes. And remember how in the transmitter we had the packet framer that put on that fixed access code. Here, we'll have that fixed access code at some point come through the beginning of the packet and go into this packet deframer. And inside here, this will be looking for that fixed code. And this runs a state machine saying, when I find that code, I know I'm beginning a packet. The next 2 bytes are going to be the length, and then some other information about the scrambling index, and then the length of the payload. And then it will decode and store that many bytes as your final payload, then compute the CRC, and then send that along as a message to this block that actually does some additional processing, so it de-whitens it, and then you can say whether or not you want it to output invalid packets or not. It'll always output valid ones, but you can selectively say whether you want invalid ones too. And then out of this, once again, you've got your packet data units, which is the original data, hopefully, that you sent over the air. And then you can send it to this block, which will print it here on the console, so you can see the raw data coming through, or you can send it to the other side of the socket PDU, and in this case, on the transmitter, you get your payload packet as a UDP packet coming out of this port. And then you can hook up whatever you want after that. In this case, it's going to be some image reconstruction and display software. So let me show you now how that can run. Remember that the E310 has GNU radio on it, and I'm hooked up from this laptop to the E310 through a network. So I'm actually able to SSH in. And so what I'd like to show you here, in this case, is a slightly different kind of transmitter. This one actually operates in continuous mode. So what I'm going to try and demonstrate to you here is that instead of having the burst mode where you just have a UDP packet coming in and you modulate that, this is also using a UDP source block, so this is sitting on a port. But the assumption here is that you always have fixed length packets. Remember how I was talking about MTU? Here our fixed size, our MTU is 1K. So that goes into the UDP port. And that actually then goes into this any block. And what the any block does, I used this previously, is if there's any data that ends up available on any other port apart from the first one, it'll preferentially pull that in and then send that out the other side. But if there's no samples here waiting, or no data here waiting, then it will always pull in what's on the first port. And so what's on the first port all the time is this GLFSR source. So this is a pseudo-noise code that's always being generated to fill in essentially the idle time of your channel, so you always have something to modulate. But as soon as a packet comes in here, it'll preferentially pull that through and insert that into the stream. So once you've done that, then you could send it to the QAM modulator block, the GMSK block, the PSK block. You've got a bunch of different options there, and send that through to the user. But instead, I wanted to essentially unpack what the PSK block does underneath and represent the individual steps that it performs on the data. So if you look at those individual steps, the first thing it does is unpack the bytes to bits, which is this pack to unpack thing. And because in this case I want to use QPSK, that means I want to take 2 bits out of the data stream and convert that into a symbol. So I do bits per chunk 2, so I take every 2 bits out of a byte, and then it goes through the map function, so it remaps the value to this sequence here, which is actually gray coding. So if you think about the constellation, as you go around the constellation, you only want 1 bit to change, which will minimize errors. So this is gray coding, And then there's differential encoding, which means that the receiver doesn't have to be synchronized to the transmitter. It only looks at the differences between the phase shifts, not the phase shifts themselves. And then, because you need to select a certain number of samples per symbol, you need to interpolate. So this is the interpolation factor here. And then finally, to actually turn it into an IQ stream to send to the radio, you use chunks to symbols. And this essentially maps your symbols that have been processed up to this point into the constellation points. So if you look at the symbol table, it actually uses a little bit of Python here. I've got this constellation object, which is something within GNU Radio that represents a DECT constellation, and you just ask for the points, and it will return a vector of 4 complex values that represent your 4 points around your constellation. And so out of that, you've got your IQ stream, adjust the amplitude a little bit, and then you go into your USEP sync. Now I've left one thing out here. Can anybody hazard a guess as to what I've left out? Something here. I've left out quite an important part of this modulation stability. Filter, exactly. I don't have a filter in there. So if you turn that off, you can see that, oh, I never included it to begin with. But yes, the DPSK block, the last step is doing the pole shape filtering. And that's pretty important because it's at least at the very least, it gives you a pretty clean spectrum. So this doesn't give you the cleanest spectrum, but I did that because I was trying to get as much performance out of it, and it turns out that pretty much the most expensive step is the FIR filter at the end. And if you don't optimize that in machine code, or you don't offload that to the FPGA, it can on an embedded device, if you're trying to run at very high bit rates, cause quite a bit of CPU consumption. So I just turned that off for the case of this test. So now, let's say I've developed this flow graph on my laptop, but I want it to run on a different machine. In fact, I want it to run on this embedded device. So I've got the Ethernet hooked up, and I've got this run remote block, and you can see here that in run remote, you basically give it your standard SSH login information. So root at the IP address, and then dot is the directory from which you want to run things. And you just drop that block into the flow graph, and when you execute this flow graph, this will inject some code into the generated Python that'll have it actually shipped over SSH. So first it'll SCP it over to the destination, and then it'll SSH it and run it remotely. So if I run this now, it's in GHub I just want to make sure that I'm not running anything else here. Okay. So if I run that now, it'll open up this window, which is actually a session running on the E310. And it just starts up like a normal USEP program. And as you can see here, each of these bursts that's going through the burst tagger is a payload packet being sent over the air. So now if I, you can see the red lights on, so it's sending data. And what I'm going to do over here, actually, before I run the decoder, I'm just going to show you that there's a signal going out over the air. I'm really excited because I got this new laptop and I can finally run GR-Phosphor on it. So it looks pretty cool. Let's see, there we go. So that's Wi-Fi, but let's look at our frequency here. What is it? Like that. So that's coming from the E310. If I move the antenna around, you can see that it's changing a bit. So as you can see there, it's not a bursty transmission, it's continuous. And so, so it's injecting basically most of the time the pseudo-random sequence, but then every time a video frame comes in, it shows up. And I'll show you the code in a minute. This here is actually another SSH session that I have tunneled into the embedded device. And this is the Python code that connects to Video for Linux, does the segmentation, the packetization, and sends it through. So it's running in verbose mode. It tells you the number of bytes in a frame, and then periodically gives you this throughput. So in this case, it's 0.2 megabits per second. So it's really not particularly taxing on the channel. And then on my laptop, I also have this other Python code that's waiting on that UDP socket to get the frames to reconstruct the video. So now if I run the receiver, I'll close this one, and if I run the receiver on here, which is this one, that's what I showed you before. Then you can see there it's printing the packets out, so it's actually getting stuff. This is the spectrum we were looking at before. This is tuned into that same spectrum, and then we've got our complex baseband up the top, and well, that's just the raw complex baseband, so it hasn't been corrected for frequency or anything like that, but you can see that there's definitely a signal there. And if we switch over to the web, the decode view, then you can see the line of video. Oh, cool, and you get the echo effect as well, nice.
Send the picture of the spectrum through the spectrum.
Oh. There we go, there it is. Happy, Moritz? Okay, so in this case, we're actually only using 1 megasamples per second. You can see there, as that was running, on the receiver, it was decoding all the frames and showing them. So the receiver is some Python code, it reconstructs these packets, and it uses OpenCV. It has a nice little library. You can basically, remember these are motion JPEG packets. So you can't just draw them on the screen, you need to have an image decompression library decode the MJPEG frame. And OpenCV does that in 2 lines of Python, which is really convenient. So as you can see there, the frame rate wasn't particularly good, the resolution wasn't particularly good. That's because our channel is quite narrow. So if we want to up the ante a little bit, it actually helps to do some raw C++ instead of using GNU Radio. And this sort of process that I was showing you before, this one here, it's actually pretty trivial, right? You either have a packet coming in or you don't. If you don't, then you just send the PN sequence, and then you basically do these mappings, and it's really not that complicated to write C++ code for. So let me show you what that looks like quickly. That's the receiver. I'll show you that in a minute. I have to mount the drive first. So let me actually demonstrate that to you now. So instead of running it remotely from GNU Radio, I'm going to start that up. So I'm going to turn off that transmitter that we started remotely. I'm going to start up the source code here. So it's just a fairly simple C++ program that uses UHD directly. I just call it modem, and you can give it a sample rate, you can give it a gain, a frequency, you can give it the latency with which to schedule packets in advance, and that's usually going to be dependent upon the hardware latency. So there's time from when you make the call in UHD to the time the packet actually gets to the radio. Any smaller than your hardware latency will mean that your user will be starved for information to send out, and you'll get underruns. So you put the latency in there, and then this idle duration you set, which is essentially the length of your idle packet. So it'll send out an idle packet, check whether there's data available in the UDP socket, and at the end of that, it can either schedule another idle packet or actually put your user payload on to be transmitted. So we can run that. And here it's running now. It's done a bunch of tests to measure the latency of the hardware. And then here it's just periodically measuring how long it actually takes to do the hardware send calls and prints out some timing stats. But that's running now. And I can switch back now to the Python video transmitter. And here I'm going to stop this now, and I'm going to turn everything up. So right then it was 320 by 240 at 5 frames per second, keeping every 2 out of 3. But now I'm going to go with the defaults, which should be 640 by 480 at 10 frames a second, which should look a little bit better. Not quite HD, but the packet sizes are much higher now, and that's 1.3 megabits. I've run it up to 3 something, almost 4. The modem's actually running at 4.2 megabits per second. So you can fit quite a bit more in there. So now on the host side, I'm going to run the receiver, which is this one. Make it look a bit nicer. And this is pretty simple too. You just got your source. It goes into the MPSK receiver. Rotate the constellation, and then you basically decode the constellation, take which point is appearing, do the differential decoding, do the gray code unmapping, unpack those symbols into bits, and then again send them to the deframer and out the socket. So it's the reverse of what we were doing before. And so if I run this one, oh, did I already run that?
Well, what frequency are you running at?
This one should be running on 910. I think it's just programming the FPGA, so it will just take a moment. Any questions while it's programming the FPGA? No? Okay, so that's our constellation then, and as we've got an AGC up the front, so as I move around it's going to try and correct for that. And then if we switch to the, there we go, I think it's looking a lot better now, and in fact the latency is not terrible either. But yeah, the frame rate's better. In fact, if we check the stats again, on the video side of things, that's still only 2 megabits. So you could up the resolution on this, you could up the frame rate on this, because you've still got quite a bit of space in your 4.2 megabit pipe to fill. Additionally, if you added forward error correction on there, you added some convolutional code, that could be used to fill it out as well, and that'll give you some gain on the receiver as well. So you can look at the waterfall there. It's just your normal kind of looking waterfall, constellation. It's kind of cool when you turn into lines as well. And this is all obviously looking quite nice because the transmitter and receiver are next to one another. And there are certain other things that I haven't done, like channel equalization and other things that will help when you're in an environment, especially when you're moving it around on a drone. So that's further research. And just to finish up then, what I'm going to do is I'm going to quickly mount the I'm just using SSHFS to mount the file system of the E310 on my laptop. And then I should be able to show you the code here. So a lot of this code actually is coupled together from 2 different pieces of code. The first one is from the old UDP source block in GNU Radio, which is the receiver, as well as some of the code in Kitchen Sync, which is a UHD utility tool that exercises a lot of the UHD API. So I'm just going to skip ahead a little bit to the main function here just to give you an idea of how it works. So essentially you just pass in the parameters first off, and you can see here it'll be interested in things, as I said, like the frequency, gain, rate, payload size, latency that you want to achieve. And then it goes about doing all this code, which isn't particularly interesting, but it sets up a UDP socket to listen on. Once the socket is set up, then it'll actually create the usurp device. So it'll create the device handle, and the cool thing is that you can either use this on a PC and hook up, say, like a B210, or you can run this on the E310 and it'll work the same in both scenarios. You can set the master clock rate if you need, the sample rate, pick your antenna and all that jazz. And then once that's all done, this bit here actually will go through and test some of the latency, so it'll call down to the radio and ask for the time, and we'll do this many, many times and measure the average latency of that call, because that's used a little bit later on. And then this is the interesting part. So remember how we had that constellation object in GNU Radio that had those 4 points? This is essentially that point, and then you reconstruct a constellation here. So I've started experimenting with different data types, so whether it was a floating point format, or whether it was a complex floating point, or complex shorts, so fixed point values. And in this case, I ended up using the fixed point value because you don't have to go through any sort of conversion when you send it down through the layers to the radio. But essentially, you just generate your PSK constellation because it's fixed. And then essentially now you have a lookup table. So that becomes really quick. And then some more testing. And then it actually goes into the big main loop here. So the first thing that it does is it just, waits for 1 second to see whether whether it needs to print any statistics out. And the next thing it does is poll the socket to see whether there's actually data available to send or not. And then it decides whether or not it's going to send that pseudo random sequence as an idle packet or actually send your user packet. And if we skip ahead, then this is the case where it's actually going to send some idle packet data. And what I'm trying to illustrate here is, remember how in the flow graph we went from the GLFSR source and then the unpacking and then the interpolation and the gray coding and all that kind of stuff. This is essentially exactly the same thing, but it's more or less 1 or 2 lines of C++ code. And so you can prototype quite nice in GNU Radio and make sure it works, but then if you want to get some extreme performance, you either have to move things into the FPGA, you have to use machine code to optimize it, or as a first step, just try it in raw C++. So this function here is actually generating your GLSR bits, because it's just essentially a mask, a seed, and then you have a shift register, and then you loop through. So this will loop through extracting a certain number of bits that you need, construct your symbol. This is the lookup table for your gray coding, and then you just basically do the index on that array using your symbol. That'll give you your gray coded symbol. Then your differential encoding is simply this line, which is just using the mod function. And then that gives you your final symbol that you then use it as an index into your constellation. And then you've got your final IQ value to put out onto the wire to send to the radio. And then you just loop for the number of samples per symbol, and you add it to your final buffer that's going to be sent out to UHD. So it's pretty simple. And then I haven't refactored this, but for the sake of illustration, hopefully you can see that in fact, in this loop here, this is going to take your payload that came in on the socket, extract the bits out of that to make a symbol, and then do exactly the same thing to generate your IQ stream to send out. And remember, in this case, you can either pick whether you want 16-bit complex samples or floating point, and it has a performance impact if you go floating point. And then that's it. You've got your payload packet, and down here, all you've got to do is call send on your TX stream within UHD, and then it's sent out over the radio. And that's it. And so from that, you can go from, in this case, 1 mega sample per second, 1 megabit per second to 4.2. And then if you use a modulation scheme like QAM, then you get more bits per symbol. So, interesting things to experiment with there. And then, finally, the streamer, I won't really go through this in any detail, but this is the Python code, just to, illustrate very quickly what's going on. With V4L, you make your video device, you set the format, you set the FPS, you create the buffers, and then you call start, and that's all you got to do. It's so easy. And then down here, you just go read and queue, and it gives you a binary buffer that represents your image data. And then this additional code here puts it through the packetization process here. It adds that header format that I was telling you about, so the size, the 4cc, the sequence number, frame size, packet length, offset, and so on. And then at the end of all this, you just send it out a UDP socket, and that's it. And then the C++ programmer sees it. And then it's just the reverse on the other side, Python state machine, decode it, send it through to OpenCV. So that's that. Any questions? No?
Will this end up on GitHub eventually?
Yes. So that's the current state of the project. And I mentioned a couple of future directions. But hopefully that's give you an idea of how you can achieve this sort of simple packet-based transmission, digital transmission using GNU Radio. So thanks. And actually, I think that brings us to the end of this evening as well. So if there are any other questions or announcements, now's a good time. Yes, we have one up the back. Do you want to come out the front?
I'm David Witkowski. My call sign is W6DTW. And how many people went to the Maker Faire recently? So last 3 years we've done an amateur radio booth at the Maker Faire. Did it again this year thanks to Barrick, K6BZ back there, and a bunch of other folks. Thinking about what we're going to do next year, we really would like to. We got a lot of traffic on SDR and GNU Radio Companion. We had a table with that. A lot of people asking questions. We're really thinking we want to double down on that for next year. So no actions right now except to let you know that we're thinking this, and maybe if you want to start contemplating something big and cool for next year and get you there and get other people to be part of that. At some point we'll have more information. They don't typically announce Maker Faire until sort of January time frame, 2016, but that gives you lots of time to come up with great ideas. So I'll be looking to come back at some point and recruit. If you have interesting projects, I'd love to hear about it. That's all. Thank you.
Thanks, David. All right. Well, let's thank Surya and Moritz. And so yeah, hopefully in a month we'll be back up in the city. We might have some interesting work shown by Josh. I'm really looking forward to that. And keep an eye on the event page, on the Meetup page. And thank you to you all attending this evening here physically, and to all the people out there in internet land. See you next time.